Hi, my name is William Corwin with the Department of Energy. I'm the Structural Materials Lead for the Office of Advanced Reactor Technology. I'd like to talk to you today about some of the work that we are hoping to get you guys to do this year under the Nuclear Energy University programs, particularly in the area of advanced structural materials. To start off with, make sure everybody's clear. Structural materials are absolutely critical for advanced nuclear reactor technologies. We are involved in the Office of Advanced Reactor Technologies, ART, in developing a number of nuclear reactor systems. And the types of advanced materials that we are talking about are critical for high temperature and very high temperature gas-cooled reactors, sodium fast reactors, fluoride salt-cooled reactors, and any of these other high temperature Gen 4 type reactors that are being developed. The type of structural materials we're talking about are those for pressure boundaries, reactor internals, heat transfer components, and whatnot, and they have to perform for the entire design lifetime of those components. In some cases, that's the full life of the plant, 60 years for most of these advanced reactor systems. In some cases, lesser time, for instance, for heat exchangers and whatnot. But nonetheless, it's a challenging performance period, time, and temperature combination. So the performance of these metallic alloys under the long times and high temperatures that are being required of them is what we are examining under the ART program. All right, the work that we're doing under ART certainly supports the overall objectives of the Nuclear Energy Roadmap. The specific objective is to develop advanced fast reactor technologies for deployment in the 2050 timeframe, and the specific pieces of that we're addressing are to develop the improvements of affordability of this class of reactors, as well as to develop sustainable nuclear fuel cycles. In particular, today I'd like to talk about some of the work we're doing on advanced materials R&D, specifically the development qualification of materials for advanced fast reactor systems, and this would include both the classes of ferritic martensitic steels as well as austenitic steels. A typical reactor that we might be looking at would be the Advanced Fast Reactor 100. This is a small modular reactor size system, typical of the type you might put on a small grid with limited needs for on-site refueling on the order of 250 megawatt thermal, with a core life of 30 years and a plant life of 60 years, so you'd only be doing one refueling. Factory built, transportable from the factory to the site, and it's going to involve innovative technologies and advanced materials for things like affordability, safety, etc. Now, we have been involved at DOE in the development of advanced alloys for several years now, and in particular, the rest of the talk, I will be talking about some of the austenitic alloys that we have been looking at. Starting in about 2008, we looked at a range of materials, the goal being to provide structural materials for advanced reactors, specifically fast reactors, but they could be used with other types of advanced reactors, which have better high temperature strength to enable higher thermal efficiencies and provide improved design and safety margins. The materials that we started looking at, and if you look down in the lower right corner where I'm poking at with the pointer down here, you can see some of the materials we've been looking at. The advanced high temperature ultra precipitation strengthened materials, alloy 709, I'll talk about that extensively, as compared to the 316 stainless steel, which is the base material that is currently in the ASME code. And if you look at this blue shaped space on this radar chart, you can see the kind of properties, particularly high temperature strength creep, that we were looking at as baseline materials, and we're trying to improve on that. So what we've ended up doing, come on, hello chart, there we go. We ended up doing a down select of this material about 2 years ago from the other candidates because it showed on the whole the full palette of improved properties, but specifically it showed a substantial improvement in strength. Now, alloy 709, nitrogen stabilized, niobium strengthened austenitic alloy, has about twice the creep strength of 316 stainless. So if and when we're able to get this in the code, it will provide designers a dramatically enhanced material that they can use. Again, increasing their design envelope and their safety margins for the reactors that they can build with this stuff. 709 is based on the 20 chrome 25 nickel composition. It was originally developed for power boiler applications. Has excellent oxidation resistance at the kind of temperatures that we are looking for. And you can see, if you look at the variety of microstructures that are shown, these are post-creep microstructures after 5,000 hours at 750 C. And you can see that they still display a very nice coverage of precipitates both in the matrix and in the grain boundary, which provide for strengthening of this material without undue embrittlement of the material. We're very pleased with the way this material looks heretofore, but we don't have all the answers for it yet. We have done a lot of preliminary testing on it, and we have clearly shown that it does have the enhanced high temperature mechanical properties we're looking for. You can see here multiple heats that we've already tested, looking at creep strength versus time, and you can see it is about a factor of 2 better than 316, which is currently in the code. So we're focusing on this as one of 2 materials. We also have a ferritic martensitic material, but that doesn't enter into the NEIP, so I'm not going to go into that today. There are some things that are particularly important for this class of materials. Actually, any of these classes of high temperature materials, fatigue and creep fatigue, are very dominant fracture mechanisms, failure mechanisms that are going to be operative over the reactor component lifetime. And these are illustrated at the microstructural level by some of the micrographs that are shown here. On the left-hand side, you can see the kind of transgranular cracking that would usually begin at the surface that would be associated with pure fatigue loading, as compared to the intergranular cracking that would initiate deeper in the specimen from creep fatigue loading, and that you see with 650 C with a 30-minute hold time. So these are the types of behavioral components that we've got to look at, particularly the ones with hold times that take a long time to assess. You really can't do the laboratory testing over the extended lifetimes that the components are going to have, and this is what we're going to ask you guys to take a look at for us. So we have 2 different, fairly closely related, but certainly separate topics that we want you to look at. The first one, under 3.1, is to look at the type of mechanisms that would be required to support the design of the fast reactors for 60-year life, specifically related to the establishment of ASME code design allowable stresses. And these are things that are based on stress to rupture out to 500,000 hours, as well as tertiary creep and stress to cause 1% strain out to 500,000 hours. But we can't test to 500,000 hours. You can't do that. Even graduate students don't live that long. So we've got to go ahead and put this thing into test at the laboratory scale. Like all good metallurgists, we like to test at higher temperatures, for instance, say 700 C, even though we may be operating at 550 C. We're going to test at shorter times, but we have to understand what the mechanisms are for the creep and creep fatigue deformation, things like microstructural evolution, the type of damage, for instance, grain boundary cavitation and whatever, that goes on to be able to provide the guidance that we can do the extrapolation of the laboratory data out to the full lifetime, 500,000 hour, effectively the number of hours that exist for a 60-year reactor life, with confidence. And so that's what we're going to be asking you guys to do. The second topic, similar but different, also looks at how to extrapolate laboratory data out to 60-year lifetime, but this part of it looks at the flaw evaluation procedures and what is required to disposition the detected indications or flaws that turn up during in-service inspection. We also need to understand this relationship from laboratory to in-service conditions required to develop schedules for in-plant inspections. They're clearly going to be different than the LWR cousins that we are moving upward in temperature from. And we need to be able to extrapolate the subcritical creep and creep fatigue crack growth data from the accelerated conditions that are produced in the laboratory to what is going to happen over the extended lifetimes of these actual reactors. So we need to be able to take what is developed, understanding the creep and creep fatigue crack growth mechanisms that we can get from the laboratory specimens such as compact tension, and translate that in time and geometry to the subcritical flaws that would exist in pressure boundary components over the reactor operating lifetime. So specifically what we're asking you guys to do is the following. We have 2 different but closely related code qualification activities that we want you guys to work on this year. creep and creep deformation and grain boundary cavitation mechanisms for alloy 709. And the outcome we are hoping to get from this is to provide a mechanistic-based, validated approach to extrapolate the creep and creep fatigue data from the accelerated test conditions that you can get in the laboratory to the long-term fast reactor operating conditions that are needed to support the extrapolation of the ASME code stress allowables out to 500,000 hours. So that's topic number one. Topic number two is to understand the fatigue and creep and creep fatigue crack growth mechanism, also for 709, that will provide validated approaches to extrapolate subcritical crack growth data from the laboratory out to the real components in reactors over their lifetimes. So the proposals we're looking for, and we'll do these one at a time, under RC 3.1, creep and creep fatigue deformation grain boundary cavitation mechanism, we're looking for proposals to develop a fundamental understanding of the deformation mechanisms involved. These are things like dislocation or diffusion-controlled creep, microstructural evolution, damage mechanisms, grain boundary cavitation, for instance, of 709 at the elevated temperatures under creep and creep fatigue loading conditions to be able to allow us to intelligently apply and interpret the data from the laboratory and accelerated testing to the lifetimes that we need for the extrapolation. The research should focus on both the similarities and differences of the characteristics between the accelerated test conditions and the actual operating conditions of the reactors. Come up with strategies for data extrapolation. And I might add, you get extra points if you can come up with approaches that include novel experimental and or characterization methods. The second category deals with creep and creep fatigue growth mechanisms, crack growth mechanisms for 709, and we're looking for proposals to develop, again, fundamental understandings of the mechanisms for subcritical crack growth in the same alloy at elevated temperatures under the same type of loading to enable us to apply and interpret the data from the laboratory tests to the field. Proposed research should focus on, again, similarities and differences of creep and creep fatigue subcritical crack growth between the accelerated lab conditions and the fast reactor operating conditions, as well as between the as-received materials and the materials that have undergone aging in service. Extrapolation strategies for the crack growth data obtained from the fracture specimens in the lab need to be developed for application into the field. And once again, we're looking for approaches that might include novel experimental techniques and characterization methods, as well as validated flaw evaluation analysis techniques. That's really all I had to say in prepared remarks, but I would be glad to talk with you all about this, as well as our technical point of contact. His name is Sam Sham, a very knowledgeable guy in this area and heavily involved with high temperature codification activities within ASME code. Sam's at the Oak Ridge National Laboratory. So if there are any questions on this, I think we're going to open up the floor for questions, and we'll be glad to answer those if you guys have some.
The first question is, why alloy 709?
I'll try that, Sam, and if you want to add something, you go right ahead.
Sure.
709, well, we're looking for 2 additional alloys to add to the ASME code palette of materials for high temperature reactors. Right now there are only 5 qualified materials from which you construct high temperature reactor components. There's 2 stainless steels, there's 2 ferritic alloys, 2 1/4 chrome and 9 chrome 1 moly, and there's alloy 800H. That's it. There's no more. And they all date in terms of their being added back to the 60s and 70s, except 9 chrome, which came in, I think, in the late 80s, Sam. Correct me if I'm wrong. At any rate, they all are relatively, well, they're all very mature materials, relatively low strength, and they certainly, we know that there are materials with higher capabilities. So back about 7, 8 years ago, DOE launched an activity to screen out what some of the potential improved materials might be for that. There was an extensive wide funnel that we looked at lots of different materials, 1 ferritic and 1 austenitic material, and we wanted to look for ones that had higher creep strength primarily, but without sacrificing the other properties, things like weldability, ductility, fracture resistance, microstructural stability, et cetera, et cetera. And it turns out that after several years of study and down select, it turns out that among the austenitic alloys, 709 came out on top. Sam, you got anything to add to that?
That sodium compatibility is also a key for the application of this material. So therefore, that 709 sort of have overall capable performance.
Yeah, I forgot. Considering that one of the principal applications of this alloy would be for sodium fast reactors, sodium compatibility is clearly one of those multiple characteristics we wanted to make sure we did maintain in moving forward with this material. That's not a requirement for the ASME code, but it is a requirement for the potential application we're looking for.
Do you have any concerns about environmentally assisted cracking or stress corrosion cracking for this alloy system?
I don't think that we have any for the high temperature coolants we're looking at. That's typically not common for those. And we don't envision these, well, I'll say that. I don't think that we have envisioned these for use necessarily with LWR systems. But who knows what the vendors might come up with. I don't think certainly that the ferritic materials we've been looking at in the parallel studies would have that problem. And with the high chrome and high nickel contents of the 709, I would say it's highly unlikely we would have that problem. Sam, do you know anything about stress corrosion cracking in this material? Obviously, that would be in a water environment.
I'm not quite familiar with the water environment but we haven't really seen any indication of that in sodium environment. But of course, that if there are data to suggest that there is a concern, then obviously that we'll be very much interested in looking at that.
In any case, it should be emphasized that our primary concern with moving forward with this material is in support of higher temperature creep strength, higher temperature design margins for the advanced class of advanced reactors. This work would be nice if it would support advanced LWRs, but that's not the focus of this work.
Is there any interest in ferritic, martensitic steels in this program?
Absolutely. We have a comparable pathway, and we have been developing an advanced version of grade 92 with an optimized, slightly optimized chemistry and a thermomechanically treated microstructure. And we do have studies going on with that, but the NEIP itself does not include activities on that. We are doing that in the mainstream program, but not under this NEIP call.
Are you also looking for uncertainty analysis due to difference in time scale and environment between lab and the actual reactor?
I think that's an inherent part of any type of basis for extrapolation. We're really looking for the mechanistic basis that would support both these topics in the area of extrapolation. On the other hand, there clearly will be uncertainty. One can never predict things out to orders of magnitude further than we're going to be able to have the data that we've got. So that would be a piece of it, but not the focus of it.
Are you looking for creep behavior of weldments too?
Yes, that would be a piece of it. I think that the work primarily has focused on base metal, but weld reduction factors and understanding how the welds behave in this material is an important thing. Sam, you got anything to add on that? That's a particular bugaboo, I know, if we get it wrong.
Yeah, well, as far as this core is concerned, we really want to address the base metal. Obviously, that weldment will be of interest, but probably that is not within the scope of this core. And down the line, we will also look at weldments as well.
All right. Well, clarification. We're really looking for base metal in this call. In the greater scope that we're looking at for advancing these materials and moving them into the code, we will have to consider weldments, but please focus on base metal in this call.
What about HT9?
HT9 is a very interesting material. It's been around for a long time. It's an old material in terms of generations of steel. It's a 12 chrome, 1 moly steel that has been used for high radiation environments, typically clad in duct. Been around since the days of FFTF and earlier. It does not currently enjoy code qualification for nuclear construction for high temperature reactors. It is a material of interest. It's a British steel, and something that for some of the applications and systems that people are developing may be of interest, but it is outside the scope of this call, and we're not going to consider that for this particular NEO.
Those are all the questions we have. Thank you, Sam. Thank you, Bill. We will be reconvening at 3 o'clock p.m.
Before you turn that off,
Go ahead.
just one last thing. If anybody else comes up with additional questions they couldn't think of in short notice, you're certainly welcome to contact me or Sam after the fact. We would be happy to get back in touch with you via email or whatever.
Bill and Sam's contact information is on the nup.gov website. You can look under the R&D tab under Technical Points of Contact to find that contact information.
Send us some good proposals, guys. We're rooting for you.